the second episode in the stats playlist. Today we'll be looking at this theorem. I claim A is a matrix n by n that's composed of the column vectors of A like this. Then the null space of A transpose and the orthogonal complement of the column space of A are the same. Basically, this equation here. We begin the proof by letting S equal the null space of A transpose A, and then letting some vector y be an element of S. Okay, this now implies that the matrix A transpose y is equal to 0. Ladies and gentlemen, this is clearly just the definition of the null space of a matrix. We then decompose the matrix into its columns. Okay, very straightforward step. I've just made the matrix in its form of columns and transposed it. So it's literally the same thing. This then implies that it can be written like such. And then we will come to the end of the proof by writing for any I vector A times y is equal to 0. And now, ladies and gentlemen, you can see that this is the definition of the orthogonal complement of A there. So therefore, y is also an element of the orthogonal complement of A, which implies that the null space of A transpose is equal to the orthogonal complement of A. Prof. Berger, I will now pass it over to you to prove the converse on this side here.
I will now be proving the opposite of what Simon just said.
Conversely,
you're going to have to cut it there because I don't understand. Conversely, if y is an element of the orthogonal complement of A, this implies that y bar, well, y vector is orthogonal to every column of A. Which implies that A y bar, well, y vector transpose is the 0 vector, because this is the formula of the null space of A. Therefore, if we take the transpose of all of this, which is equal to this implies that y is an element of the null space of A transpose.